Yeah, welcome to another video from me, and as you can see, there's still a lot of things going on the bench. Behind me I still have the AT board here, but I had to dig into some other stuff, just temporary, some normally day-to-day repairs, and I do this from time to time. People have asked me if I do this for a living, and I really don't. I work as a senior computer professional and has done for most of my life, but I had this as a hobby for many years, and I do have the formal education. I am both trained as a technician and I'm an electronics engineer from back in the day. So sometimes these things get thrown my way, both from myself, from friends, family, neighbors and others. They come, can you look at this? And more often than not, I say yes. And I've done a lot of these fixes from time to time in between videos and other stuff. And I've decided now I will try to make some movies, YouTube flicks about this, and I will post these in between the other videos. Sometimes they will be long, sometimes they will have more in-depth explanation like this one that hopefully you will enjoy. This will give you a basic fault finding course, very basic for many of you, but it's a bit of a picture of the process I'm following when I dig into something that I don't have the schematics for and I don't know much about. But let's start with the theory and the walkthrough of this first. So let's dig into the boring part, and then we get back to the bench afterwards. Yeah, it's pretty interesting that at the same time that I'm trying to grow my channel, I do present you with probably the most boring theme ever on a YouTube video. I will present the office desk. But actually this is a circuit from a motor-controlled height-adjustable office desk. And this mechanism is made by Linac, and they probably make some good stuff because they are still in business, so they must do something right. And this was bought back in, I think it was 2004, and it has worked flawlessly for many years, and it has been a very sturdy mechanism. But it started that you have to do some reboot from time to time. You had to cut the power and plug it back in. And that made me suspicious about capacitors and other stuff that was not working optimally, or some other thermal issues. So I had to take this apart, and I have done that. And basic fault finding 101. And I'm going to take you through this. It might be boring, it's obvious to most of you, but fault finding is about having a process. It can be, you have to either make a sketch or a mental picture will do in most cases. You just have to make up your mind what this circuit really should do and what is missing for it to accomplish what you should do. So, ironically, fault finding is mostly about thinking outside the box, but you have to start with a bunch of boxes anyway to sort things out. Just doing fault finding in the blind, it can work, but it's not the best way, it's not the most efficient way. And throwing parts at something without really thinking about is this a culprit to what you're experiencing is not a very good process, it's not a very environmental friendly process, and it's not an economical good process. So you start with the basic pieces. What is the controls, the input in your circuit, and what should be the result? So the start and the end goal. And you have to add some more pieces anyway. You do have to have a power supply with fuse, filters, regulators, so on. You do have to have some protection circuits. Actually, you don't have to, but I know it's there because if you block the functionality of the desk, it will actually stop. So if you are in a danger of hitting something or destroying something, it should go into protection mode. And you have to have some control logic, even though it's basic up-down, you do have to have something that controls this and takes the input and do something with it. And you have to have a motor relay or other power control to hit this motor. This motor is a DC motor, so probably it's just reversing the polarity to make it go up and down. And you have to tie the pieces together. You have to have a connection between the up-down switches and the control logic. You do have to have a way to make the motor relays work, and the motor relays has to be connected to the motor. You have to have the protection circuit from feedback from the motor power draw or something. You have the protection logic to cut into the control logic. And of course the power supply needs to supply all parts of this with power. And you have to ask yourself, what possibly could go wrong in this picture? And that is when we start with the board, and it's about identifying some of these pieces. And you do have some known pieces, and you do have some unknown pieces. You have the control input, you have a power regulator, you do have some rectifier diodes, you do have a smoothing capacitor, you have some output relays, you have some power transistors, you do have a huge resistor, you do have some connectors for the power supply, you do have some connectors for the motor, and you do have a bunch of other stuff on this board. What is this actually doing? So you have to start with the basic and identify what you are going to find out. And let's start with the individual building blocks as far as we go. This is the power supply part, and you do have an LM3 Sutton. It's a very familiar component. It has been used for ages, and I used this the first time back in 1985 when I made my first basic power supply. And this is a circuit that can deliver from 1.2 to 3.7 volt. And you do have some gimmicks to make it even more flexible than that, but it can take a power draw about 1.5 amps, and it's a sturdy workhorse. Of course, to give it 1.5 amps with 37 volt input, you do have to have a huge heatsink and a good connectivity. And this board is partly aluminium, so it's probably have good heat drain capacity, but it won't be that kind of power draw on this. So we do know that this is probably only controlling the control logic. And you do have some rectifier diodes here, and this made me puzzled because you do have a space here for another regulator, and you do have some more control logic and stuff here. And you also have part here for some more relays and stuff. But you have a double set with rectifier diodes. Is this an oversight, or is it because it's glued in a special way here? I'm not sure, but I do think they have gone overboard with the rectifier diodes. But anyway, this is components that is easily replaceable and easily measurable. You do of course have a huge smoothing capacitor, and you do have some other capacitors down here that's probably is basic part of this one. And when we go further in, you do see that we have an op amp here. This is a dual op-amp, LM358. It's a very commonly used component. It's a very simple amplifier, or it can be used as a comparator. And in this case, I do think it belongs to this resistor here that is working together with this to form the protection circuit. Because I think this small resistor here acts as a shunt resistor. And this is a very small resistor, not in physical size obviously, but in resistance. It's probably able to drain several watts, but what we can see here is that the special markings where you have a silver ring, this is not gray, it's silver, it marks a very small resistor value. So first band black, second band yellow, and third band silver. You can use one of these online calculators, there is a lot of them, and I do remember most of this color code stuff from back in the day, but I do go back and check this when I'm not sure, and especially on the less common ones as this one. And this is just 0.04 ohms. It's a very small value, it will be a very low voltage drop, and then it's good to have this op-amp. Because it's registering just small differences between the output, you will get a huge output difference. And if we go further along, you do have some NFET 8 high voltage switching transistors here, and these are very convenient parts because they can be controlled with a logic level signal on the gate, and they can take a power here. It's about 48 amps for continuous use, and you can pulse it with 144 amps, and that with a drain source voltage of up to 60 volt. And of course, the reason why you can have this huge draw on these transistors is because they have a very low resistance when they are turned on, so it won't be much of a power loss internal in the components. These, I think, measure out just fine. You do have a special contraption here with a resistor or capacitor. I am not really sure. I might have to dig into that, between the gate and the drain here. And the next part is the relay, and these are ordinary components. This shows a picture with through hole components, but it's the closest picture I could find. It does have a 12 volt markings on the actual coil, so it probably is controlled by the MOSFET transistors, and this is an SPDT. And that means single pole double throw. Single pole is just that it's one single switch, and it can switch between two different outputs. So this can go so, and it can go so. And you do have other variants. You do have the double pole double throw. You do have double pole single throw. You can have single throw single pole, and more different variants than that. But I do think the relay are just fine. And you do have the capacitors on this board. And of course, 2004, it's in the middle of the capacitor plague timeline, but Nichicon probably made some good stuff. You can see here, it might seem like this is bulging, but I'm taking this picture here from some new components I found online. And it doesn't differ much. And this cross up here is of course the security valve. If this starts boiling, it should release its content controlled and not explode. But I'm going to measure this anyway. This is the smoothing capacitor for the power, and it's probably situated straight to the diodes for the rectifier. And if you're not familiar with these kind of capacitors, you can see here it actually has a minus marking here, and these ones are marked down here. But if you're not familiar with that, you can see the corners here on this plastic frame. The cut corners always marks the positive side, and the square corners mark the negative side. And the markings of these capacitors are this. I might draw over this, but this is 10 microfarad, this is 100 microfarad, and this is just 1 microfarad. And you do have the voltage markings here that's either marked with an E or a V. So this is 16 volt, this is 6 volt, and this is 50 volt. And the 50 volt one is the one that is placed here. So this is probably on the input side of the LM317, and this is probably on the outside side of the LM317, and this I'm not sure, but probably it's just a reservoir piece for the comparator dual op-amp thingy. And I did find a burned resistor, or not burned, but it has been very hot resistor on this board. And when I measured from this point and to this point, I got a very high resistance. I also tried to measure to this point and get a very high resistance up in the 1.89 mega ohms. So there is something strange with this. And the markings here was 361, but I actually read it upside down at first and thought, okay, the 19E resistor, that is 19E in the AIA96 range, and this should be 1.54 mega ohms, and that's not very far off, but I found some more components on this board that was marked the same, and I also noticed this one when I put on my magnifying glassings, so I did turn it the other way and find out that it was 360 ohms about. And this is an easy mistake to do. You have to make your markings on your components right, and the same with the capacitor here. You do have to know what is marking the value and what is marking the other stuff. And these capacitors here is always marked in microfarads, even though it's not stated microfarad that is here. It's the normal way to do it. And the same with these resistors. You do have to know that there are 4 at least different way of marking these resistors, so you do have to find your way. And of course, we need to look into this part of the circuit when we do the fault finding. And this part of the circuit is actually in the control circuit. We can find this back here. This is this resistor here. And it's in conjunction with this MOSFET and this relay, probably this relay too. And it has been burning very hot, as we can see around here on the edges. But let's head over to the bench and do some real-life measurements on this circuit. This time it's, of course, I say this often, something different. This is a card from office desk where you have this motorized function to change the height of the desk. And this card has been working flawlessly. I do think the board is from, as you can see here, it's from 04 here, and I think it actually was bought in 2004 or 2005. I can't really remember. And you can see there are some faults here. This has been very hot. You do have some other resistors here that is meant to take high wattage, but it's not this one. You do have a capacitor here. It's a bit bulking, but I don't think it is. It's actually a Nichicon capacitor, and you have some small ones here. And this has not been leaking because the pads, they are totally shiny and fine, I think, all of them. So I do know that this is bad because it have gotten hot. I'm going to desolder this one to make a good measurement and also to see what is underneath here. I'm also going to desolder this relay here because this trace down here it's actually the solder mask has loosened a bit, so I want to check that there is no fault underneath here. So first thing, desolder this one, and we take it from there. I do think it's lead-free solder on this board, so I do some additional normal lead solder on this, so they will have a lower melting point. It's easier to desolder this without lifting any traces. Yeah, I do use my good desoldering braid that contains flux, so it's easier to suck up the solder, but these are soldered on the surface. There are no holes, so you can't suck up the solder that's between the flat surface and the board. So you do have to do some additional heating and trying to just pry the component of the board without damaging the traces beneath. But this seems like quite the sturdy board, so this actually goes quite well. The problem here is that there is very little space around this relay, so to avoid damage the plastic and melt the relay I have to be very careful, and I also try to use a screwdriver to make some pressure while I desolder this, because it's 2 legs on one side and 3 legs on the other side, and it's quite rigid, this component, so it doesn't flex. That did not prove to be as easy as I thought it would be. I at least need to get it up on this side so I can tilt it a bit. And this is plastic, so it's no good to use the hot air either. Maybe if I use 2 soldering irons and have a third hand helping me here. In the end, a combination about heating and prying helped me get these out. But now we can see here I have exposed this track here. And it's fine, but this relay is probably okay, so I won't bother with that. And this resistor here, that should be 360 ohms, Let's see. I can confirm I have two other of these here on this board. This one is the same, 359.7, and this one 359.8, 1.6 kilo ohms. So this is definitely bad. And it's mega ohms, not kilo. So I do need to desolder that one too. I do think that will be easier. We don't have to take as much precautions as we did earlier. Oh, it's already off the board and I just soldered on one side. Let's measure this one when it's out. Okay, then it's the right size. So this here was already loose. Yeah, and that's something quite special. It means that the resistor itself was okay, but it was loosened from the solder on one side, and it actually was some soot or something in between the soldering and the other stuff, so it didn't make contact at all on one side. That's really strange. To repair this, it's possible just to find out where this track leads, and this track here is possible also to just solder in a normal resistor. Then we can lift it a bit from the board as well. And that turned out to be quite easy. One side of the resistor went to one of the poles on the drossel to the relay, and the other is just bridged over some other pads, and it's easy to reach. So we just put in the new resistor as shown here. But then it was the capacitor, and we are going to use our PeakTech capacitance meter and check. I do seem to remember that this side here is the positive and this side here is the ground. Yeah, the clips just kept falling off, so I hold this against the poles manually. This was the plus side. It's R 0.14 and it has a capacitance of nearly 2000. So this capacitor is probably in fully working order and there is really no need to replace it, but we are going to do it anyway. This is a 2000 microfarad 50 volt, so it's not exactly the same, but it should be equal enough. And let's test it. Yes, it's about 2000 microfarad. The question is this one better? ESR 0.0 ohms, 0.1 ohm ESR. Let's check the other ones. Measuring in circuit is of course never accurate, and all of these capacitors measure actually a bit low testing in circuit, so I do think I have to desolder them to check if they really are that off in values. And how far off are they, you might ask? And this one that should measure 100 microfarad are 85 microfarad, not alarmingly low, but I do think it's better to change it because this is not easy to reach once it's mounted back in the desk. Yeah, I think I'm going to change all these capacitors. Then it's done, and I'm going to change that resistor here. And then the question is, the big capacitor, I do think it's good enough, but I do think I'm going to change that anyway. Yeah, we are starting to make a mess on the bench here. I just have some El Cheapo capacitors here. And we had this one here. It was 1 micro and 50 volt, the same as these guys. And we had this one that was 10 micro, 16 volt. It's this one. And you had this one that was 6 volt, 100 microfarads. And 100 microfarads, I have 50 volt. It should be this one. And we also need to replace the resistors. And here I do have some 360 resistors, and I do think these are 1 watt, but I'm not sure if they was 1 or half watt. But what I'm going to do is I'm going to mix these up, put 2 and 2 in parallel, and I'm going to then put 2 and 2 in series, so that together should be the approximate same value as one of these. And here we actually saw that we had plenty of space and we had 2 possibilities for how we was going to solder this in. So solder something like this together, and that should be about it. And we also have to solder back in the relay, so that I will have a pad here to solder it on. And I'm going to freshen up the solder. Yeah, first I'm going to actually tackle this one. It's not a wise idea to have this much mess on the bench, but it is what it is. That should be a solid one. And I'm not very used to surface mount soldering, but this is not high precision work. This is kind of large tabs on everything, so I do think that this will be okay. Like so, and the next side. And of course, as the amateur I am not filming the actual soldering, I'm just filming the top of my hand, but I'm using the screwdriver here to push on the tabs to make them stick better to the solder. Yeah, that should be good in there. And then it was this resistor thingy, and it won't look very pretty, that's for sure. And I can, to make this a bit safer, I can take and put this into a shrink tube. Yeah, maybe first we can measure it out and see if it's okay. Yeah, 350-ish. That's how accurate this resistor was. And see what the other one was. 359. That should be okay. Yeah, I will just thread this piece of heat shrink tube over the resistors, so they won't short out anything on the board if it gets pushed on or if it sags or something. There is nothing much else going on over here, so I do think I can solder this in without disturbing anything. I will just tin these leads so it will be easier to solder them. And then I will just reheat the solder pad and the solder that's already on there and hope it sticks. And I do need to heat a bit more. These pads and the relay are quite the heat sinks, I think. That is that side taken care of. And then it was this one here. And I'm bending the ends of the leads here as a hook, so it should be better grip on the soldering pad, because this is quite the huge pad that these are going to be soldered into. Yeah, that should be okay. So if I now measure from the rest of this pad to this pad here, yeah, we have the 350 ohms. So that should be okay then. And then we have these capacitors, and maybe we should check them with the meter and see how they fare. These 3 are the new ones. It was a bit difficult with these clamps on this meter. Now it's 1 kilohertz. I have to put it down to 100 hertz. Yeah, 9.6 and very low ESR. This is the 100. Yeah, 92.51. This should be the 1 micro. Yeah, it is measuring as 1000 nanofarads. That's the same. Yeah, I'm going to put some fresh solder on the pads here. And this is the method I always use for surface mount capacitors. I have a generous amount of solder on the pads, and then I just put the capacitor on, give it a bit of pressure and reflow the solder, and voila, it's okay. So this always works for me. Somebody else maybe have another method that's working better, but with a large iron and not the best eyesight, this works every time. And the last one is up here. And it's a bit close to some resistors, so I have to be careful not to heat them too much. And I do think I did make a solder bridge here, so I do have to use some desoldering braid to clean up that. Oh, that should be okay. So that's this one. And this one, I have the option. I can use this one. That is a known good one, of course. And I can use this one. And the old one measured out quite good, but it did have a slightly higher ESR than the new one. And also, this is mounted inside the table leg on this table, so it's very cumbersome to get this out if it fails again or if it's not right. So better safe than sorry. So I'm going to solder in this new capacitor, and I'm just going to bend the legs straight out and make them into fishing hooks so they will fit better onto the pad. Yeah, before I finish this up, I'm going to measure that nothing has happened with these MOSFET transistors, and I'm just going to measure that there is no shorts on them. And there are no shorts on them, so they are okay. Then all the components that we need to replace are replaced, and I'm also going to show you one more bit. And that's this one. This actually, I got the rest of the thing today. And this is kind of special, if you will follow me on this. This is a board that is just a fuse, and it's a capacitor 330 nano that is standing as noise suppression, and you have a 1.25 amp fuse. For good measure, I can just check the fuse if it's okay. It should be, yes. And you can see on this board here, you actually have a place for a drop-in fuse here. So this board could have been replaced with just taking these leads and placing them here and entering a fuse. But then there will be no noise suppression on this. So I do wonder if this is something they have just done to make a modification after they have got some trouble with the authorities, or if they just messed up something. Because as you can see here, this is just an inline socket that stands between these two that could have been the fuse. So if you have added a noise suppression capacitor in here somewhere, this would have been the same circuit. So I don't know if that's what they was thinking. And this one should be screwed in like so. And I'm just going to check that I didn't mess up anything with my big capacitor. No, it fits just fine. It's plenty of space in here. So this is ready for testing. This is the remote control cable with the up and down switch. And this is what's going out to the motor on this. And you can see on this board you actually have place for two more relays. You have place for one more of these power regulators. And you do have some other things down here that I'm not sure what to make of. But also you have this series resistor here that you can have one more of. And you can have one more of these MOSFET transistors over here. So this controls one of the two relays, and these relays are SPDT, so they are single pole switches with two positions. Yeah, and you can also see you can have a totally similar plug, so it's maybe to control a desk with two motors. This actually has a single large foot in the middle. So that's it from the bench, but hopefully this will now be going back and the desk will start working again. Hope you enjoyed the contents. This time it was about repairing this board. It was a basic electronics repair, and I tried to make this into sort of, let's call it electronic basic 101 course in fault finding. because it's about finding the process that will get you through the repair, and hopefully this did exactly that for you. And I will do a bit more of these basic electronic repair video. I do have another one that I do have to look into, and is this circuit here, so I will be doing that too and see what the response will be. So thanks for watching, hope to see you again in my next video. Please hit like and subscribe, and please watch some of my older videos. Visit my YouTube channel and browse through some of the archive there. So thanks for watching, see you in the next one.